Hey class, this is going to be your 7-8 lecture. So 7-8 is all about what happens if you get a repeated eigenvalue. And the first case that we're going to deal with is if you get a repeated eigenvalue, but you only get one eigenvector that corresponds. So the general rule is here. If lambda is a repeated eigenvalue for a 2x2 matrix A, and A only has one linearly independent eigenvector k corresponding to lambda, then the fundamental set of solutions for x prime equals ax is you get your regular x1 is k e to the lambda t, and then we do a little something like reduction of order here to get x2 is equal to kt e to the lambda t plus another l e to the lambda t, and the way we're going to find that l is by solving the system of equations a minus lambda I l equals k. So remember, k is the solution to a minus lambda I k equals 0. So once we find our k, we're going to make that the right-hand side and find our l. We'll just get started with an example here. So let's see. Let's let a be equal to -6, 5, -5, 4, and we want to solve x prime equals ax using our eigenvalues. So just like normal, we're going to find our eigenvalues. We take the determinant of a minus lambda I. We're going to set it equal to 0. And the determinant of a minus lambda I is going to be -6 minus lambda 5, -5, 4 minus lambda in determinant form. And in polynomial form, that's going to be lambda plus 6 times lambda minus 4 plus 25. And when you expand it all out, you get lambda squared plus 2 lambda plus 1. But that means our equation is lambda plus 1 squared equals 0, which tells me lambda equals -1 and -1. We get a repeated eigenvalue. So we're going to proceed as normal. So the next step here is to take a plus I, right, and multiply it by k and set it equal to 0. That's our a minus lambda I. So in this particular instance, that is going to be the matrix -6 plus 1, 5, -5, 4 plus 1, which row reduces, or really this is just directly equal to -5, 5, -5, 5. That row reduces to -1, 1, or 1, -1, whichever way you want, which tells me that k is just equal to 1, 1, or any constant multiple of 1, 1. And I only get one eigenvector. What could happen in this instance is if our a minus lambda I, if we put that out there and it row reduces to all zeros, then we would get two eigenvectors. I'm going to do a case like that that's not quite so trivial. Here in a minute, it's going to be actually a 3x3 matrix, so I'm not too worried about that, but I'm just saying this is what happens. This is how you can only get one eigenvector to go with your repeated eigenvalue. So that means from our theorem up here, from our process, we want to find the L to find our second solution, our second linearly independent solution, and the L is the solution of a minus lambda I L equals k. So in this case, we take a minus lambda I is still -5, 5, -5, 5. I haven't done any row reduction there yet. And now I want to solve it with the 1's in there, so I need to actually augment it. Remember, I don't normally augment it when it's 0's because it doesn't change anything. But when we're talking about when there is an actual right-hand side that isn't 0, it matters. I'm just making sure I didn't lose a page. Yep, there I am. So we can row reduce this really, I guess we shouldn't row reduce it. We're there. We'll write the row reduction step. This is -5, 5, 1, 0, 0, 0. That's the step that I wasn't sure whether or not to skip. I'm going to go ahead and write it out. And this says that -5 L1 plus 5 L2 equals 1. And we can pick any L that works for this. We just need a solution to this. So let's pick the one that makes the most sense to us. If I divide through by 5, I get that -L1 plus L2 equals 1/5. So L2 equals L1 plus 1/5. And so I can write L as any vector with the property that L1 is free and L2 is L1 plus 1/5. But I can pick L1 to be anything I want. Remember, I just want any vector that works here, and so I can pick L1 to be 0 and get the vector 0, 1/5. That seems like the easiest of all the vectors that would work. So, going back to our system, we have x1, which we've already found. x1 is k was 1, 1, e to the minus t, right? Lambda was -1. And so now we know x2 equals 1, 1 t e to the minus t plus our L, so that's 0, 1/5 e to the minus t. And that is a fundamental set of solutions for our equation. We can check real quick, if you'd like, the Wronskian of x1 and x2. That is the determinant of let's see, that's going to be e to the -t, e to the -t, and then I'll get, that's a 0, so that's just t e to the -t, t e to the -t plus 1/5 e to the -t, which is equal to the e to the minus t, t e to the minus t's. Those are going to cancel out, so I'm just going to get 1/5 e to the minus 2t, which isn't 0, so the claim of it being a fundamental set of solutions is verified. And so then that means the general solution will be x equals c1 times x1. Uncover x1 there. c1 times x1, that's 1, 1 e to the -t, plus c2 times x2, so that's all of 1, 1 t e to the -t plus 0, 1/5 e to the -t. We could sketch some trajectories here. That would be appropriate. I actually have just pre-printed here. This is a direction field for this. If you need to generate a direction field, like I said, you can use technology, and I told you I wouldn't ask you to do it on a test. But Here's a direction field for this particular system. So if we took a trajectory where, let's see, if C1 equals 1 and C2 equals 0, then our trajectory, that would just be along this line where we're pointed at 0, right? And this other one, you would want to use some computer graphing, but if I let C2 equal -1 and C1 equals 0, the solution, or sorry, the trajectory would look a little something like this, where it also points at the origin. And in fact, if we look here, you know, one of the common questions is what is the limiting behavior? So as t goes to infinity, all of these pieces go to 0. So x approaches 0 as t approaches infinity. Sorry, when I say 0, I need to make that the origin, not just 0, right? Because x is a vector. So then the other thing I want to show you is what happens if you have a repeated eigenvalue, but your eigenvector is actually, you get repeated, or not repeated, but you get linearly independent eigenvectors. And it's also worth showing a 3 by 3 system. So we're going to do x prime equals 0, 1, 1, 1, 0, 1, 1, 1, 0, and times x, and we're going to find the general solution. Okay? So the first thing we do is we take A, that's this matrix, minus lambda I, and we take the determinant of that and set it equal to 0, right? So the determinant of that is going to be negative lambda 1, 1, 1, negative lambda 1, 1, 1, negative lambda. Now, in terms of a determinant, this one's not exactly pretty. I'm just going to do cofactor expansion across the top there. That'd be negative lambda times lambda squared minus 1 minus 1 times negative lambda minus 1, and then plus 1 times 1 plus lambda. So let's see, we get 0 equals, I get negative lambda cubed plus lambda plus lambda plus 1 plus 1 plus lambda. Does that look right? Double checking myself here, make sure I didn't miss any places where I had a lambda squared. Oh, I think that's correct. So this is minus lambda cubed plus 3 lambda plus 2. And we could go through and solve this a number of ways. I'm actually going to kind of skip that. And the way that I would solve this, if I were going to solve this, is I would guess a solution. I would notice that if I plug in, let's see, if I plug in a 2 here, what happens? Then I get negative 8, and then I get positive 6 and positive 2. So, and then I would divide out by lambda minus 2, and I'd get a quadratic. And when it's all said and done, you end up with lambda 1 equals 2, lambda 2 equals negative 1, and lambda 3 equals -1. So now in that case, we're going to do the same normal thing. We're going to take a minus 2i, so we've let lambda 1 equal 2, and we're going to take a minus 2i times k1. I'm going to use subscripts here, k1, and set it equal to 0. So we take our matrix, which is -2, 1, 1, 1, -2, 1, 1, 1, -2. And then we row reduce this. And the easiest way to row reduce this, I'm going to flip the first and third here. -2, 1, 1, 1, -2, 1. I'm going to subtract row 1 from row 2. So that's 1, 1, -2. That'll be 0 minus 3, 3. And I'm going to add to row 1 to row 3. So 0, 3, -3. Well, I've got that beautiful setup. I think I'm going to go ahead and add row 2 to row 3 to get row 3 as all zeros. And then I'm going to rescale row 2 like so, leaving row 1 alone for the moment. Now I'm going to go ahead and subtract row 2 from row 1. And so I get 1, 0, -1, 0, 1, -1, 0, 0, 0. So I have x3 is free, x2 equals x3, and x1 equals x3. So I should have said k instead of x. I'm just used to x. So k1 here should be equal to 1, 1, 1, or any multiple thereof. So then lambda 2 equals -1. Go ahead and pop that up there. So we have lambda 2 equals -1. Also lambda 3 equals -1. We're going to get a twofer on this one. So when I plug in -1, that means I have a minus -1i. So that's a plus I times k equals 0. That's what I'm trying to solve. I'm going to try to find k2 and k3 here. So when I put that in, I actually get 1, 1, 1, 1, 1, 1, 1, 1, 1. Right? And so this row reduces actually easier than the other. And I get 2 rows of zeros, which means I have 2 free variables. So I have x3 is free, and I have x2 is free, and I have x1 equals minus x2 minus x3. Now, because I have 2 free variables, I can write this, well, regardless, I can write this as k equals, so x1 is -x2 minus x3, x2, x3. I can write that like that if I want to. I've been skipping that step here. I've just been finding something that plugs in and works. But I need to find 2 linearly independent ones, and it actually turns out to be really easy. But in order to see why it's so easy, it's kind of nice to split this into -1, 1, 0 times x2 plus -1, 0, 1 times x3. And so then I can see that for one choice of x2 and x3, I'll get a k1. And I'm actually going to take k1 to be equal to -1, 1, 0. That's the one where I let x2 be 1 and x3 be 0. And I'm going to take k2 to be equal to -1, 0, 1, which is where I let x2 be 0 and x3 be 1. I could have taken any other linear combination and it would have worked so long as I didn't take the same one twice. But always take the easy one. We're choosing for our own convenience here. And so now we've got a k for every lambda. So I can put this k with that lambda and that k with that lambda. Even though those lambdas are the same, it's all right if we get linearly independent eigenvectors. So our general solution, x equals c1 times x1. And remember, x1 lambda 1 was 2 and k1 was 1, 1, 1. So that's c1 times 1, 1, 1 e to the 2t plus c2 times negative 1, 1, 0 e to the minus t plus c3 negative 1, 0, 1 e to the minus t. And that's both how you can find the solution to a 3×3 system of differential equations using eigenvalues, and what happens when you get a repeated eigenvalue but linearly independent eigenvectors. That's really all you need to know for 7.8. Good luck.